In the last two videos on percentage composition, we have calculated the percentage compositions of formaldehyde and acetic acid given their molecular formulas. And if you paid attention, you would have noticed that these two compounds have exactly the same percentage composition, though they are two entirely different compounds. Formaldehyde is a pungent gas at room temperature, whereas acetic acid is a liquid if the room temperature is around 20 degrees centigrade. And formaldehyde is toxic, and acetic acid is used in food preparations in the form of vinegar. Yet they have identical percentage compositions. Why? For that, you have to look at their molecular formulas again. The molecular formula of acetic acid is C2H4O2. And what do these subscripts tell us? They tell the number of atoms of each of these elements present in one molecule of that compound. Of course, they also tell the number of moles of atoms of these elements present in one mole of that compound. And between these subscripts, the greatest common factor is 2. And if you rewrite the formula of acetic acid, after dividing these subscripts with 2, you would get a new formula that looks like this. And in this formula, the subscripts are shown with smallest integer numbers. Such a formula is called empirical formula. So what does the empirical formula of a compound tell us? It tells the simplest ratio between the atoms present, between the number of atoms present in one molecule of that compound. So the empirical formula of acetic acid tells that for every carbon atom present in that molecule, there must be 2 hydrogen atoms and 1 oxygen atom. That is the guarantee that this empirical formula gives. But it does not tell you the actual number of atoms of each of these elements. So try to understand the meaning of empirical formula. Now let us look at formaldehyde. Its molecular formula is CH2O. Now how do you get the empirical formula from its molecular formula? You have to divide the subscripts in the molecular formula with the greatest common factor between them. And in this case, the greatest common factor between these subscripts is 1. So if you divide these subscripts with 1, you will get the same numbers. So the empirical formula of formaldehyde is also CH2O. Now what does the empirical formula of formaldehyde guarantee us? It guarantees that for every carbon atom present in that molecule, there must be 2 hydrogen atoms and 1 oxygen atom. Now if you look at the empirical formula of formaldehyde and that of acetic acid, you would notice that they are one and the same. That means in their molecules, the relative number of carbon, hydrogen and oxygen atoms is the same. They contain carbon, hydrogen and oxygen atoms in the same relative proportion in their molecules. And that obviously means they have the same percentage composition. So if 2 or more compounds have the same empirical formula, they have the same relative number of atoms in their molecules of the same elements, of course, and therefore they would have the same percentage composition. To make sure that we understood the idea of empirical formula and percentage compositions by mass correctly, let us ask ourselves some questions. If 2 or more compounds have the same empirical formula, what can we say about their percentage compositions? As we have seen here, if they have the same empirical formula, then they must have the same percentage composition. Now the next question. Do we need the molecular formula of a compound, or is its empirical formula sufficient to determine or calculate the percentage composition of a compound? See, formaldehyde and acetic acid have different molecular formulas, yet they have the same percentage composition because they have the same empirical formula. Therefore, the empirical formula of a compound is sufficient to calculate its percentage composition. Now the third question is, if two or more compounds have the same percentage composition because they have the same empirical formula, is the vice versa also true? If the percentage compositions of different compounds are the same, should they all have the same empirical formula? Of course. Now the next question is even a bit more interesting. Can we identify the compound just by looking at an empirical formula? See, there are two types of compounds, covalent compounds and ionic compounds. In covalent compounds, we have small discrete group of atoms called molecules. And a molecule of a covalent compound is represented by its molecular formula that indicates the actual number of atoms of each element present in one molecule. Take the example of formaldehyde and acetic acid. This is the molecular formula of formaldehyde and this of acetic acid. But these two have the same empirical formula. So if I just give you the empirical formula CH2O and tell nothing else about it, can you identify the compound? No, you will not be able to figure out whether I am talking about formaldehyde or acetic acid because they both have the same empirical formula. But on the other hand, if you take carbon dioxide has the molecular formula of CO2 and its empirical formula is also CO2. And there is no other compound with the same empirical formula as CO2. So in this case, we can clearly identify the compound just by looking at the empirical formula. So in case of covalent compounds, it may not be possible to identify the compound just by looking at an empirical formula. Now, in ionic compounds, there are no groups of atoms called molecules. Ionic compounds contain crystals of different sizes, and in each crystal, an enormously large number of oppositely charged ions are arranged in a pattern. Take for instance sodium chloride. It is composed of sodium ions and chloride ions. Then what should I put for the subscripts of sodium and chloride ions? I do not know of a number. But I know that in each sodium chloride crystal, the ratio of the number of sodium ions and chloride ions is 1:1. That is, for each sodium ion there is a chloride ion. That is why we show the formula of sodium chloride as NaCl. This indicates that the ratio of sodium and chloride ions in sodium chloride is 1:1. It does not represent one molecule of sodium chloride. There are no molecules in case of ionic compounds. So, in the formula of an ionic compound, we show the subscripts in the simplest ratio. And that is exactly what we do in case of an empirical formula also, right? So that means in case of ionic compounds, whatever formula we are using to represent the compound itself is its empirical formula. So for an ionic compound, the formula itself is its empirical formula. You take any ionic compound, you will find in its formula the subscripts in the simplest possible ratio. And the second thing is, we do not have two different compounds with the same formula, two different ionic compounds with the same formula or the same empirical formula. For example, Na2Cr2O7 is sodium dichromate. With this particular formula, there is no other compound. There is only one compound with this formula, that is called sodium dichromate. And if you look at the ratio of these subscripts, they are in the simplest whole number ratio. So the interesting thing with ionic compounds is, the formula used to represent the ionic compound itself is its empirical formula. And secondly, we do not have different ionic compounds with the same empirical formula or the same formula. Therefore, in case of ionic compounds, we can identify the compound just by looking at its empirical formula, which itself is its formula. Hope that makes sense.